Hello and welcome. It has been a while since I made a video, but I hope the wait was worth it for this one. This video is a continuation of my series on canonical flows. In case it is unclear, let me explain the motivation behind making this series. The reason for studying these canonical flows is that they really allow us to zero in on a specific flow phenomenon, like a boundary layer or a mixing layer, and make sure that we are capturing and understanding the true flow characteristics. More complex problems are just composites of these canonical flows, so we really need to make sure that we have these simple cases nailed down before moving on. Often when you tackle a complex problem first, it is difficult to see where, or even that your simulation is wrong, if you don't understand the simple cases first. Let's consider the flow around a car, for instance. This will be a composite of boundary layer, free shear flow, rotating meshes, etc. It is best to study all of these independently and then combine them. In this video, I will also continue my exploration of applying adaptive mesh refinement, or AMR, to single-phase incompressible flows. The method I have been developing involves using passive scalar transport as the refinement field. You can think of injecting a tracer or dye into one of the inlets and refining the mesh at the interface. This method has various limitations for more complex simulations, but works very well for the free shear flows which I have been and am continue to explore. In this video, a rectangular co-flowing jet was studied. The effects of the initial mesh resolution and adaptive mesh refinement were studied. In the table shown, you can see the cases that were investigated, 4 without and 3 with AMR. An additional LES case was also simulated for purposes of developing the case, but the properties weren't carefully set up, so it will only be used for visualization and demonstrative purposes. The following plot shows the number of cells in each case, along with the equivalent cell count needed to resolve to a similar extent without AMR. Please notice that the y-axis is a log scale, so the delta between the cases is actually much larger than it appears. This plot shows the cell count for the AMR cases at different times during the simulation. Please note that the maximum cell count was at 5 seconds for all the cases. The base mesh for these simulations was created fully using blockMesh. Because I haven't found too many videos on the subject, I will be releasing this also as a separate video so that it can quickly be referenced in future use. The first thing to find in the blockMesh file is the location of all the vertices, 32 in this case. Here I've created an animation so you can see their locations in space along with their numbering scheme. The numbering scheme of the vertices is the hardest thing to keep track of, but it is vitally important for specifying blocks and boundaries. The block mesh I define here will extend from -3 to 3 meters in the x and y directions, and from -6 to 6 meters in the z direction. The jet is 0.2 meters tall and wide. The blocks are basically individual meshes that are put together to create an overall mesh. They are defined by the vertices of 2 opposite faces. For instance, here with block 1, we can see that vertices 0, 1, 12, and 11 define one face, and vertices 16, 17, 28, and 27 define the opposite face. To define the block, we simply list these vertices along with the number of divisions in the x, y, and z directions. The same for all of the rest of the blocks. Please note that the interface between the blocks need to have the same number of divisions, and that the order the vertices are listed need to match from one face to the next when defining a block. For instance, if I define one face by starting with the top left vertex and then go counterclockwise, I need to do the same for the opposite face. Once the blocks are defined, it is important to define the boundaries. Again, this is done by listing the vertices that make up the faces that you want to be a boundary. You also need to list the type of boundary you are defining. This may be a patch for an inlet or outlet, wall for a wall or some other object, or empty for a symmetry plane. The best way to really wrap your head around this whole process is to look at the animation I showed in the beginning with the vertex labels. The code is provided in case you need it, and really go through and see what each line of blockMesh file is referencing. Now I will take you through the results of these simulations. Here in the first slide, you can see a slice through the center of the domain for each of the cases. In this slice, I have also plotted a slice of the mesh so that you can see how the mesh is refining at the interface of the flow coming from inlet 1 and the flow coming from inlet 2. I will soon show you the full-length animation for each case, but it is useful to look at this diagram and note how the ring vortices are resolved by the cases with finer mesh and don't even appear for the coarser cases. One important point to make is that the refinement strategy I used is the one on the right, or octree. It may seem like the diagram and upcoming animations are quad tree, but they are in fact octree. Quad tree is just the two-dimensional projection of octree into a plane or slice. These are the animations of the scalar transport for each of the cases along with the slice of the mesh, so that you can see how it is dynamically adjusting. While I am showing this animation, it will be a good time to mention that I used a KOmegaSST turbulence model because I had a case I wanted to modify to make this that was using this turbulence model, but a more appropriate model may be the K epsilon model if you're specifically interested in free shear flows. The idea has been to try to validate all of these canonical flows simulations using the KOmegaSST because it has good near and far wall behavior, and ultimately I plan on running simulations that need to capture both conditions. And here is the LES simulation, so that you can see all of the multi-scale turbulence associated with a co-flowing jet. Next I will show you the velocity profiles for cases 2, 4, and 7. This data was attained by plotting the velocity along 13 different lines, as shown in the figure below, in pair view. This data was then exported into Excel and analyzed using a code I developed in Python. Again, this will be provided with all of the case files in the GitHub repo linked below. It is interesting to note that case 4 had the most cells, at around 450,000. Case 7 had around 350,000 peak cells, and case 2 had around 140,000 cells. But you can see from the velocity profiles that cases 2 and 4 have much more similar results than that of case 7. This is because of the adaptive mesh refinement performed on case 7 actually makes the results more similar to a case with around 9 million cells. These results really show the power of adaptive mesh refinement. You can get the results of a case with 9 million cells for running a case with the computational cost of around 350,000 peak cells and probably closer to around 200,000 cells average. It truly brings down the cost from a level requiring a supercomputer to do any serious CFD calculation to something that's doable on a pretty normal home desktop with plenty of RAM. As always, thanks for watching. Please like, subscribe, and share my content if you found it useful and think that others would also find it useful. It is really the only way to get others to see that this content exists. If you have any comments or suggestions for future videos, please leave them in the comment section below. Once again, thanks for watching. Please be on the lookout for more future content to come. Have a good day and goodbye.